Thank you very much. Thank you for having me here. Yes, so I will be talking about the ocean, and I will be talking about ocean circulation and how the ocean moves around and swirls around, and everything we put in the ocean so it actually gets along in the currents and ends up somewhere. So I can make this a sad story. I can make this a story about pollution, about how we as humanity are really polluting, are putting all this garbage into the ocean, and the ocean is just taking it up for us, and it's accumulating more and more. I could also make this a fun story. I could make this a story about rubber duckies, about very cute small rubber duckies floating on the surface of the ocean, and how they are exploring for us and going where no duck has ever gone before. So I will make this a fun and a sad story. But above all, I will make this a fascinating story. I will make this a story where I hope to really convey to you the amount of fascination I have for the ocean. All of that ocean that we don't know. So 70% of the surface of the Earth is ocean. 97% of all the water on Earth is actually salt water within the ocean. And the most staggering fact I always think is that there have been more men to the moon than to the lower half of the ocean. We really have no idea what's going on there. There's still so much to learn just from the way that the ocean moves, the way that water goes from A to B. Right? And there's so much to marvel at and so much to explore. And that's really what I hope to convey here tonight to you. Of course, we do know some things. It's not that we don't know anything about the ocean. And already for centuries, people have drawn up maps like this. So this is a map of typical ocean surface circulation, right? And what you see are arrows, and the arrows are kind of like the average way in which water flows around the ocean. Water flows from A to B, mostly driven by the wind. Almost all of this is the action of the wind on the surface of the ocean, whereby water just moves along. And you see very clearly things here like the Australia current and the Gulf Stream up there, and they're red because they transport warm water from the tropics towards the poles. And then you see these blue ones, like the Benguela here in Peru, and they're blue because they transport cold water from the poles towards the tropics. And everything seems to turn around, right? It all churns like a beautiful clockwork where things go around in these basins. Right? So this is what we call advection. This is the way that the mean currents of the ocean slowly take water from A to B. And for a very, very long time, actually almost shamefully long time for us oceanographer, we thought that this was the way the oceans work. But since the dawn of satellites, basically, we have a much better understanding that on top of this slow advection, there's what we call eddies, eddy mixing. Eddies are whirlpools. They're not particularly small. Well, to an oceanographer, they're small. They're 50 to 100 kilometers in diameter or so, and the ocean is full of them. They're small things rotating. They can go both clockwise and anti-clockwise, and the ocean is basically this chaotic, bubbling soup of eddies moving around there, right? And it turns out that the eddies are really crucial if you want to understand better what the ocean is doing with the things that we throw into it, as the story of the rubber duckies will tell us. So the story of the rubber duckies is that in 1992 there was this freighter, big freight ship, going from Japan across the Pacific, which is across the side here, towards Seattle. And basically halfway it hit a storm. And that's not unusual. Freighters hit storms very often. And what happened then is that quite a few of the containers fell overboard and fell into the water. That's also not unusual. That happens also quite often. But what is very special about this one storm and this one container freighter is that there was one container on board that had a rather unusual, remarkable load. In it were 29,900 packets of what we call friendly floaties. Friendly floaties are bath toys. They were 4 really cute little bath toys. There was a red beaver, a green frog, a blue turtle, and a yellow duck. And 29,400 times 4 of these cute little toys spilled into the ocean, right around here. That's your ducky there. Of course, in folklore, everybody forget about the red beavers and the green turtles and the blue frogs. No, the other green frogs and blue turtles, and everybody focused on the yellow duckies because duckies are yellow, duckies are cute. And there's this guy called Donovan Hone who wrote a really fascinating book about it called Moby Duck. I really recommend it. And the book is not only about oceanography, it's also about anthropology. It's about why duckies, why rubber duckies, why yellow rubber duckies, and what it all means in our culture. But that's really not the topic here. I'll focus on the ocean, and I'll focus on what happened next. So 29,400 rubber duckies into the ocean. And really all at the same moment and at the same place, right? I mean, it might have been a few hundred meters. We don't really know what happened. Due to insurance policies, it's still a little bit unclear what exactly happened. But all of these duckies there in the middle of the ocean, same place, same time. What happened next is that they were stopped all over the place. They got really everywhere. They got all along the west coast of the US. They got even into Australia. They got to Japan. They even got to the east coast of the US and Europe. And that's quite surprising if you think about it, right? It's not that all of these duckies that you throw in the ocean at essentially the same time, that they all end up at the same place. But rather they get scattered all over. Why is that? Well, enter the eddies. Enter the eddies, right? It's the eddies. It's actually the chaos driven by the eddies that has dispersed all of these all these small rubber duckies. And it turns out that you really need these eddies to try and understand where water goes from A to B. Right? So these rubber duckies in principle would have been an awesome tool for studying ocean circulation, right? Except for that we can only find them when they are at the beach. So they don't give us that much information. It would have been really cool, right, if they were not launched in 1992, but somewhere in 2012, and they would all have a GPS sensor. So that we could really track where they would have been. And if you would find a duck in the ocean, on the beach, you wouldn't only have a duck, but you would actually have a record of where that duck has actually been. Well, the duckies didn't have that, but the good thing is that we oceanographers have been doing exactly that for the last 30, 40 years or so. For the last 30 years, we've been throwing into the ocean these things. They are drifting buoys, and they are essentially a beach ball on the top. It's this size or so, with a GPS and an antenna, so that a satellite phone is essentially. And that sends its position every 6 hours. So it floats with the currents, and every 6 hours it transmits its position back, and we know exactly where it is. And then it has this huge, what we call sock. And that's really to make it more representative of the upper ocean currents, right? So the ocean currents, of course, are not everywhere the same. Here it's very much driven by the wind. And as you go down, the effect of wind becomes less. And by just taking this this sock there, what we call you integrate out the Ekman spiral. That's the fancy word for it. And we've been doing that for 30 years, and if I say we, that's really including me. We've been throwing in these buoys and just watching where they go. And if you now just take an area of the ocean, so you're such as here near Sydney, between here and New Zealand, and plot all of the trajectories of all of the buoys that have been going through in the last 30 years, to get something like this. So this is a kind of spaghetti diagram that the ocean really is. It's not this nice cartoon with the simple arrows and the smooth arrows of water just simply circulating around. This, I always tell my students, is what the ocean looks like. It's chaos out there. It's mayhem. It's just a complete spaghetti of buoys going everywhere. And sometimes you see something of a current, like here of New Zealand, or here you should say the current a little bit. But most of it is just pure, or almost seems random. Of course it isn't random, because if it would be random, then we wouldn't have garbage patches. Right? Speaking of garbage patches, of course, these are plastic, and they do drift in the ocean. So they are very much similar to the plastic bottles, to the bottle caps, to the plastic bags that get into the ocean and flow from our beaches into the open ocean. Which is why last year, me and my colleagues, we decided to use this data set to actually study the garbage patches. Because they behave just like plastics. They flow in the ocean with the currents, with the only difference that we know where they are. So we can use these trajectories to say something about where, if you would start out here of Sydney, where you would end up. And it turns out that you do end up in the garbage patches. But it's not that trivial. You can't use these trajectories by themselves because they have one big problem, these drifting buoys. Their batteries last only 5 years. After 5 years, the batteries are gone, and they still float. They're still perfectly capable instruments in some way, but we just don't know where they are anymore, so we can't use them anymore. So we can't use individual trajectories. If you would take one of these buoys or so, you would never find one that makes it all the way from Sydney into the garbage patches. You would always have to combine buoys, and that's what we did. That's what we did last year when we did the study. We actually basically knitted together short pieces of trajectory, just going from one to the other and stepping over them and making them as long as we wanted them to be. Longer than we ever needed. For thousands of years we've put these trajectories. Right? So what do these buoys look like? I mean, this is only a few in the Tasman Sea, but this is all of them over a particular year in the ocean. So this has been going for 30 years. This is all of them just slowly moving around, right? And this also gives you a nice idea about how fast the currents are, right? In some regions they go much faster than in other regions. Like here in the tropics, they go really fast, and here they kind of linger around. And here already you see the garbage patches kind of form, right? You see these aggregation of buoys that don't really seem to do anything anymore, that just linger around in these places, exactly where we know that the garbage patches are. Again, evidence that these buoys are really like garbage patches. So then, so we have this technique. We have this technique of taking these buoys, first chopping them up in short trajectories, and then knitting these short trajectories back together until we get whatever length we want, like knitting a sweater or something. And then we could do that for the whole ocean. An interesting thing we did was we wanted to know how much of whose garbage ends up where. Who's to blame for the garbage patches? That was the question that we started out with. The problem is, that's a really hard question to answer, because if you want to answer whose garbage ends up where, you need to know how much garbage everybody produces. And there's really no data on that. There's no there might be some data about the total amount of garbage produced in the world, but certainly not on a per country basis, let alone on a per region basis. So what we decided to do was to use a proxy. We used the amount of people that live near the coast to kind of tell us how much plastics there might have been into the coast, right? More people just mean more pollution, mean more waste into the ocean. And then this is what we came up with then if you do that. So you see a lot of people near Indonesia, near China, near India, also around the US, a little bit of Sydney. And then we could just seed with this, use this as our input, and just see what happens if you then integrate the plastic forward in time. If you evolve the plastics, our model plastics, based on the surface drifters, and see where it ends up to. And this is what happens. So what you see, so we're now like 5 years in or so, you see a huge patch emerge in the North Pacific. And you see an even bigger patch emerge in the Indian Ocean. That's just because there's so many people in India. But you also see one in the South Atlantic, in the North Atlantic, and even a small one here in the South Pacific. All of our oceans harbor a garbage patch. And this is known. This is not some artifact of the way that we've done this study. People that go out there measure garbage patches in all of the oceans. Even did in this one. And though this one seems particularly small at this point, our study indicates that within 500 years or so, it will be the second biggest in the whole world, just after the North Pacific. So now might be a good point to quickly discuss a little bit about the garbage patches, right? So first of all, garbage patches are not islands of trash. They're nothing like that. They're actually, if you would be out there on a boat, you'd be really hard pressed to even notice that you're in a garbage patch. Because the plastics it gets from our beach, the bottles, the bags, it quickly disintegrates. It quickly gets smaller and smaller pieces until what you're left with is just millimeter-sized pellets. Really small, kind of confetti style that's within the upper ocean, within the upper 10 meters or so, suspended, like a very thin bouillon or so of garbage, right? of plastic confetti out there. And you would really need a net to find it out and to measure it. But even then, even though you can't see it, there are more regions in the ocean where if you would take that net and you would actually haul it through the ocean, you would find more plastics in your net than plankton. More plastics than life. But that's pretty devastating to some people, and it's a nice catchphrase. I use it every now and then. I use it here. I use it on the radio. But there's a catch to it, and the catch basically is that that's partly true because there's hardly any life in the ocean in these places. The ocean is teeming with life. There's huge amount of fish. There's huge amount of that biodiversity. But almost all of that is near our coast. It's in the coral reefs. It's in the kelp forests. It's where we fish. Out here is deserts. It's the ocean equivalent of deserts. There's just nothing there, and it is because there's no nutrients anymore. It's all water. The water actually is the oldest water on the surface that you can find. And when I mean old, I mean that the water comes from the deep ocean somewhere, and then it's full of nutrients. It's full of things that plankton can live on. And as it then flows around in the ocean, it gets to the oldest parts. And there all the nutrients have just been eaten up. There's nothing to sustain life anymore. Which brings us to the reason why these patches actually form. So these patches form because the ocean circulation is not two-dimensional. Even when I showed you the arrows in the beginning, or when I showed you the buoy tracks and the eddies in the second, that was not the whole story. The whole story is actually that water can also make a vertical circulation. So water doesn't only stay at the surface, it comes up, mostly near our coast and near the equator, then moves around in the ocean at the surface, and at some point, namely these points, the ocean is pushed back. The winds actually force it backwards. And why do you then get garbage patches? Well, simply because the plastics is too light. The water can sink, the water can be pushed down by the winds, but the plastic just stays buoyant. It's like the turd that won't flush. Try remembering that one if you think about garbage patches. No, but it's exactly like that, right? It's just too buoyant. It stays up there, and there's and as then the currents move in, they bring in more and more and more plastics until you've got this accumulation of plastics. Right? But these garbage patches. I had this piece in a conversation a month ago where I said, if you want to put your plastics in the ocean, there's no better place to store it than in the garbage patches. There's no life, there's no fishing, there's hardly anything going on. The real problem of the plastics is not the garbage patches. It's actually the route from our beaches towards the garbage patches. That's where the harm is done. That's where the plastic actually interacts with our fish. That's where we get hurt by the plastic. Right? So the question then, of course, is, what is that route? Well, and you could see you could see it a little bit on this movie, but of course you're all very eager now to try yourself. You all have your own favorite experiment that you want to do and see if I would put in a rubber ducky at this place, where would it go? Well, the good thing is that you can actually do that. We made a website called adrift.org.au. I'll now show it off, where you just point on click on a point in the ocean, like Sydney here. You get a cute rubber ducky, and it will actually compute for you how tracer, how duckies, how plastics, how whatever you want, moves from here into the open ocean. It's cool, right? Yeah. Remember that we have a Facebook like button and a Twitter button. And we like likes. Yeah, so that's everything I want to say. I want to convey to you that the ocean circulation is not as simple as it is. It's not as simple as you see in an atlas with simple arrows drawing the currents. The ocean is full of eddies. They're full of what we call mesoscale, 50 to 100 kilometer or so, vortices, whirlpools that mix everything around. And it's this mixing that really makes the ocean interesting. Thank you very much.